All right, thanks everyone for coming. So today I thought we would, I know that one of the main things that I think people are interested in is kind of doing order of magnituding to understand kind of climate, Earth scale climate change related stuff, so that you can get some more intuition and grounding of like how big are we talking about, like how much energy, how much CO2, how much heat. So I thought we'd kind of dive into that a little bit more. So the first thing that's going to be just a quick warm-up one is how much fuel does the world burn? And this is trying to get to like how much CO2 is there in the atmosphere every year added by our civilization. And then I thought we would go into, and this is why we had pyramids before, the size of gigatons, particularly in Great Pyramids. So how many Great Pyramids is like a gigaton? Great Pyramids of Giza. So I thought that was like kind of a fun thing to try and estimate. Earlier today, I was actually able to get pretty close. So we'll see how you guys do. And then Anders Sandberg, who's a guy on Twitter and who's a professor at, research fellow at the Future Humanity Institute at Oxford. I was talking with him about this, and he was like, oh, one of my favorite order of magnitude things is like, if you took the Gulf Stream and poured it on like Antarctica, like how much like ice would you melt? So I thought we would kind of attempt our own version of that. So like how much heat is in the Gulf Stream, which is the current that flows on the eastern part of the United States, and then like how much ice could that flow of warm water melt? Yeah, so that's what we're doing today. We'll see if we have enough time. So first things first is how much fuel does the world burn? So I thought this would be something that like we would do just on our own. We'd take a few minutes to try and come at our best guess at this. And to help a little bit, I thought some things that might help is, how many people are on Earth and how much fuel does each person use? If you're unsure, like how much oil or natural gas or whatever do we use as a whole, maybe instead go to like a person. How much does a person in the United States use, or China, or like, sub-Saharan Africa? And just, what we're doing in Fermi Gym, this is something you got to practice, something that Venkat said, you got to practice being fast and loose and just like being bold. And like, maybe like the total answer on an order of magnitude too, so you can kind of like come from both ends. But anyway, I'll give you guys a few minutes to try and come up with your best guess of, how many pounds or tons of CO2 did the world or like humanity as a whole release last year, and what does that translate to like amount of CO2 per capita?
How many minutes would you say?
Like two or three.
Okay, that's much less than I was thinking.
Okay, if you want longer, we can do like 5 or 10. However long is like long enough for you to feel like you got a good attempt at it. Yeah, there's no, this isn't supposed to feel super rushed. Hey Sriram, so since you're just joining us right now, our first like individual question that we're working on is trying to figure out how many tons of CO2 did humanity emit as a whole last year. And one way of breaking that down is to try and guess like how much fuel or CO2 is released per person. And one way of thinking about that is maybe, if that's a little hard, what is the average size of like a carbon credit that you would buy to like offset yourself? Maybe that would help too, if you have an idea of like that scale of things. Like, are you buying like 1 pound carbon credits? Are you buying like million ton carbon credits for yourself? Yeah. Anybody still working, or is everybody about got a guess? All right. Do people want to put their guesses in the chat, or if somebody wants to say aloud, happy to hear that too. Your answer and your reasoning. Yeah, go for it. Anybody that wants to. All right. So I'm seeing. I think that's 25. Oh, that's kilograms. That's kilograms. So to convert to tons, divide by 3. So 10 to the 7. So that seems like 10 to the 7 tons. So that's 25 megatons of CO2 for Max. Other people? And Max, how did you come up with that? What was your reasoning?
Yeah, so I'm just putting this in because I feel like I should, but I'm really, really not confident in this. I was trying to think about um, how much gasoline an average person would burn.
Yeah.
And I was thinking about traveling. So I just thought the average car maybe something like 12 miles per gallon. And then I did some questionable conversion to something like 5 kilometers per liter. And I kind of guessed that the average person would spend something like five, uh, travel something like 5,000 kilometers per year. So that's 1,000 liters of gasoline burn. And then I kind of guessed that 1,000 liters is like 1 liter is equal to 1 kilogram of CO2, which is
Yeah.
probably very wrong. But then
I
that's
know.
how
I mean, that seems close enough. Sure. Yeah.
yeah, yeah. And so yeah, then 1 kilogram of CO2, and then I just multiplied. Oh, it's actually I also times it by 5. I think the average person would probably burn like 25,000 liters of gas a year, and then I multiplied by that by 7 billion, and that's how I got the number.
Great. Okay. So this is one of the, and so David White also had I think 25 gigatons there as a different guess. So I think, Max, that was a good approach. And one of the cool things about Fermi estimation is when it turns out that like, our estimation wasn't quite right, what it means is that we were leaving out like an important like extra consideration. So even when you know the estimate is off, that like still helps you learn something. So I think what you did is probably in the right ballpark for how much like fuel people use in their cars. And so I think the real interesting thing to note here, so the real answer, by the way, is 35 gigatons. 35 billion tons of carbon was emitted by the world. And what that ends up with is about 15 tons per person in the US, 2 tons per person in India, 8 billion people total. If you divide 35 by that, that's a little over 4 tons per person for everyone in the world. And I think the big thing here is that where is a lot of that going? That's going to heating, that's going to like making concrete and steel, and like, big transportation of trains and ships and stuff. And so I think particularly the heating, I think a lot of fuel is getting burned for that kind of extra stuff besides just like personal car transportation. But yeah, it is interesting that it's like tons of fuel. And I think, what David said with the like conversion between gallons of fuel and like, amounts of carbon for that is a little tricky too. And Venkat said, yeah, he didn't have a CO2 conversion. So
Yeah.
that's our scale there. Anybody have questions or comments on that before we move on?
I approached it from a home electricity bill. Like I vaguely remembered reading somewhere that the average home is like 2000 kilowatt hour bills or something like that. So multiply by 10, but then again, divide, that's a US average. And I read somewhere that US is about 10x the world. So I took off 10x again. So that's how I got there. And the other, I also threw in a multiplier because I read somewhere that home heating and cooling, which is the biggest part of home electricity, is about a third to a quarter of all energy. So I did a factor of 4 there somehow. But yeah, again, don't know how to convert to CO2 directly.
Yeah, so that's something we should maybe look up afterwards, is the like CO2 to electricity conversion. I think with that extra piece of knowledge, then you could interconvert between there. So something good to know. And if we wanted to, we could probably think harder about it, but that's not our main thing right now. So the next question, so now we have 35 gigatons. The next question is, how much volume would that take up? So if I actually took the gigatons and I converted them into a solid, maybe I like paired them up with calcium and turned that CO2 into limestone, like the White Cliffs of Dover, like how much volume would that take up? And from before, we know that like rock, and again, this is, we're being fast and loose here because we're going from CO2 to like something that's CO2 plus calcium. So that's like, double the weight. So like we're going to be sloppy there, but we're order of magnitude here. Anyway, it's about rock is about 3 tons per cubic meter, to recall. And so the question I have is, how many Great Pyramids of Giza is 35 gigatons? And so I think what we're going to do next is we'll break up into little groups and we'll try and estimate how many tons is 1 pyramid of Giza. And here's a picture to try and help a little bit. But I will.
The big ones, not the small ones.
The biggest one. Yeah.
Okay.
All right. So I'm going to pause. Okay, so ooh, now I can't see everybody else. Oh well. I guess I can no. Let's not spotlight me then. Sorry guys. I thought I was so good here, but
You might be able to call from your phone or something, and then you could mute yourself and make sure that you can see us at the same time as your iPad.
yeah, I just want to make, okay. So now I think this is maybe the solution. I just talk and it will jump to me. So great, okay. Cool, so great job everyone. Maybe in the chat, you guys can write down what you estimated for the weight of a pyramid, and then we can figure out from that how many pyramids 35 gigatons of CO2 is. Right, so Max got about 13 megatons per pyramid. How about the other group? Okay, so that, interesting. Okay, you didn't get something higher than 10 to the 5? That seems a little off. But okay, that's okay. It's fine. Close enough. It's within an order of, well, about an order of magnitude. So anyway, really quick, how would we do this? I think what everyone probably did is just estimate, you know, how do I do this? Oh, it was working before. No.
Oh, I think I got, sorry, I think my first calculation was right. I think 40,000 pyramids and 10 to the power 6, sorry. Never mind.
Yeah. Okay, I'm sorry guys, this was working earlier, but now I seem to not be able to annotate. So I'm gonna try one more time. Okay. Well, sorry guys. I guess having some technical difficulties. We'll have to do this later. Anyway, the oh, and now it's not even. Huh. Okay. Sorry guys. I seem to have messed up sharing the iPad and stuff. Oh man. Okay, let's try again. Okay, so we're here. We're going to share content. We're going to share our screen. We're going to share that. Is it working? No. Oh, there we go. Sorry, guys. There's the screen broadcast. There's the PowerPoint. And it's not working. Okay, so anyway, here are the slides. I'll figure out next time actually how to write on the slides. It was working earlier today, so I apologize. But in essence, what we want to do is we want to guess the size of the pyramids. And so we guess something like, I was looking at this by trying to count how many blocks there were and saying like how big was a block. Max said he thought how many people stacked on top of each other would it be about this high. And I think you get and you get something on the order of 100 to 200 meters tall. And then for the base, I was like, okay, it looks a little off 1-to-1. And I was first going to guess, I was like, let's say it's a kilometer. And I was like, that seems too big. It's probably a few football fields. So I was like, 3 football fields is 300 meters. So, 300-meter base, 150, 200, 300 meter tall, something in that ballpark. And then something great Max also did, which I also did, was like, well, how big is a pyramid versus a cube? And I was like, let's just make a cube, 300-meter cube, and then let's say, 1/3, 1/4 of it is a pyramid. So, some factor there. And that should then get you something on the order of, the 100 by 100 by 100 gives you 10 to the 6 cubic meters. And then, your numbers on top of there, your 3s or whatever, bump you up to 10. So I think we get to an order 10 to the 7 cubic meters cubed. And then, density of rock 3 tons per cubic meter. And so we get something like, 10 to 30 million tons. And we're talking about 30 gigatons. And so that's at least 1,000 pyramids. Yeah. Wait. Yeah. Okay. So 1,000 pyramids, but maybe 10 to 6. Yeah. Great. So something between 10,000 and 1,000 pyramids is how much fuel we burn as a civilization, more or less. Like that's how much CO2, that's how many molecules, if you gather them and turn them into stone, humanity is emitting every year. So you can think you go to all these cities and every city is just every year building a pyramid. And so you get this 1,000 pyramids all around the world, every year building more and more pyramids. So that's kind of to get the scale of how much CO2 we're emitting. I thought that was kind of neat way to frame it. So that's that. If any questions or comments before we move on.
I was mentioning before that it really does just kind of put in perspective the challenge of carbon capture. It's just the engineering challenge. It's okay, you have to build 10,000 pyramids of Giza a year. That's a huge technological commitment.
Yeah, exactly. Yeah, that's kind of why I wanted to do this, because exactly that's how much CO2 we want to sequester. And again, well, yeah, I think the sequestration targets are first 1 to 10 gigatons. I don't think you have to take all of it out, but at least some sizable fraction. Yeah, so hundreds of pyramids a year. Yeah. Mm-hmm. Cool. Okay, so next slide. Now, how much heat energy is in the Gulf Stream? This one is a little less estimated. This was just, I'm going to give you some facts. And then the next slide is figuring out how much ice that could melt. So here's a picture. Just, hope beyond hope that we can annotate here, but I guess not. So here's a picture of the Gulf Stream. You can see Florida there. So the Gulf Stream comes out of the Strait of Florida and goes up the east coast of the United States. And it's quite a big current. It's this quite warm water. And this is what, helps the eastern United States not be really cold, way up, at Canada level or higher, is you have all this warm water coming up. So a great unit to know is what's the scale of ocean currents? How much water, how much volume is an ocean current? And the correct unit is the Sverdrup. And the Sverdrup is 1 million cubic meters per second. And ocean currents are on the order of 1 to 100 Sverdrups. So 1 million cubic meters per second is a Sverdrup. And to put this in perspective, all rivers going into the ocean, the Amazon, the Mississippi, the Yangtze, like all of them add up to about 1 Sverdrup. So like all the rivers of the world is like 1 Sverdrup, and like ocean currents are like, you know, at least that much or more. So they're like, ocean's big, it's got big currents. So interestingly, the Gulf Stream, when it comes out of the strait, is about 30 Sverdrups, and as it moves up, it like sucks more water along with it, I guess, and becomes up to 150 Sverdrups. And I think the largest current is the like Antarctic circumpolar current, and that thing's also like 150 Sverdrups or something. So this is like a lot of water moving. And you know, this water, when it you know, when it starts off of Florida, is at 24 degrees Celsius. You know, it must cool down somewhat, but looking at the picture, you know, it goes from like red to orange. So, you know, we could say maybe it's, you know, 15 or something, even getting all the way up there, degrees C. So the final thing I wanted to remind you guys is that we're kind of, if we're talking about melting ice, you know, we're thinking about like calories and like latent heat of melting and stuff. And so if we remember, like 1 calorie is heating up 1 gram of water by 1 degree C, or equivalently 1 kilocalorie is heating up 1 liter of water by 1 degree C. And so if we have, you know, this like 20 degree C water, and we have like 1 million cubic meters of it per second, like that water has like some heat in it because it's above freezing there. So, you know, we could think of how much ice like you would need to melt. And I think like moving ice up to, you know, from more frozen to 0 degrees C probably also takes a calorie. And then I think actually causing that phase transition might take more. I haven't actually looked it up. So I think we'll just have to guesstimate there. But I guess, you know, one of the things you could think of is like if you had, I don't know, a block of ice in like your cup, and you poured some like, you know, 20 degrees C water on it, like would all the ice melt before, like, I don't know, would the water cool down and then some of it freeze, or would like the ice all melt? So I think like this amount of water can, like, you know, one liter of water, I don't know, how much ice could it melt if you poured on it before it all cooled down? Like half, a quarter, something on the same order of magnitude probably, or like maybe 1/10. But that was kind of what I was thinking about this. Any questions about that before we move on? All right, so then the question is, if you took the Gulf Stream and you like poured it on some ice sheet, like how much ice could you melt? And I think the intuition we're trying to get here is like, how big are these heat flows of these, like, you know, of the Earth scale, ocean scale heat flows? How much heat is actually moving with the Gulf Stream? If the Gulf Stream is changed, like how big of a climate effect could that have? And equivalently, like, I don't think there's really more heat than like ocean currents that could be delivered to places. So like this is kind of like the fastest that I think things could possibly fully melt. And so, like, you know, how big are we talking about here? And like, mind you, what actually happens with like ice sheets is they like crack before melting, and they like fall into the ocean, and like they stop, you know, then other ice can slide in. And so they don't even need to fully melt before they're having an effect. But like, you know, this is more just to get some sense of the scales we're talking about. So this was the question I kind of wanted you guys to tackle. And I think the 2 sub-questions we can ask is like, how thick are ice sheets? And then, you know, the question we want is how many square kilometers of ice could you melt by pouring, like, I don't know, a Sverdrup of water on them? And so we want to convert, you know, with that thickness, we can then get square kilometers into a volume, and we can, you know, compare this volume of warm water to a volume of ice. So yeah, I mean, I think there's there's maybe a few enough of us, we can kind of, well, I'll let everybody be in private. So